Hello, my name is Renato, and I'm going to present you my paper entitled Better Together, an Ensemble Learner for Combining the Results of Ready-Made Entity Linking Systems. I've done my research in LTS Research Center, which is based in Hanover in Germany. Entity linking, which is sometimes also called as named entity recognition and disambiguation, is the task of determining the identity of entity mentions in texts in general and link them to referring entities in a reference knowledge base, like Wikipedia or DBpedia. For example, in the sentence Jordan played for the Wizards, a typical entity linking system would link the term Jordan to the wiki page of the basketball player Michael Jordan and the term Wizards to the wiki page of the USA basketball team Washington Wizards. Entity linking is a crucial task of great relevance for a wide variety of applications, such as information retrieval, document classification, or topic modeling. And usually, high precision and recall are required if the entity linking results are to have a very positive impact on any such applications. However, the entity linking remains a challenging task because the systems differ along multiple dimensions and are evaluated over different datasets. Consequently, their performance also varies significantly across domains and corpora. For example, evaluations using the Gerbil framework have shown that the performance of the systems is highly affected by some characteristics of the datasets, such as the number of entities per document, the average document length, or the salient entity types. In this way, a general-purpose entity linking remains a challenging task. Based on the entity linking literature, we've seen that the performance also varies strongly on each individual mention in the same corpus. So, selecting the entity linking system on a per mention basis rather than for a particular corpus can significantly increase the performance. Even though the selection of the most suitable system for a given mention remains a challenging task, some previous works have shown that mentions that are difficult to link often share some common characteristics, for example ambiguity, also mentions of long-tail entities which are not well represented in the knowledge bases, or mentions recognized in short documents with very limited context information. So, drawing on these observations, we argue that effective features can be derived from the corpus, dimensions, as well as the surface form to be linked in order to predict the best performing entity linking system on a per mention basis, but using supervised models. In a nutshell, we make these following contributions. We introduce the novel approach towards meta-entity linking, where outputs of multiple systems are combined. We also propose a diverse set of features that provide suitable signals for predicting the best answer for a given mention. And we also train supervised classifiers, which exploits the previously mentioned feature set for predicting the correct links. Okay, so here I give you an overview about our proposed method. Our approach exploits n different entity linking systems operating over the same reference knowledge base, and we apply them to the same corpus of documents D. The output is the n sets of entity annotations corresponding to the n sets of entity mentions. It's important to mention that the size of each set of annotation differs since each system might have recognized different entity mentions. So, assuming that we have sets of annotations created by the different entity linking systems, the task of meta-entity linking aims at providing a unified set of annotations where for each mention, the most correct annotation is selected from the union of all those sets of annotations. The solution proposed in our work is called Meta-Entity Linking Plus and is based on supervised classification. We propose two variations, one focusing on high recall, which is the loose approach, and a more selective one focusing on high precision, which is the strict approach. For both approaches, if at least two of the systems have recognized and disambiguated the same entity mention, we predict the system to consider using a multi-label classifier. But if only one of the systems have recognized an entity mention, in the strict approach, we predict if the link is correct using a system-specific binary classifier, and for the loose approach, we include all the annotations recognized by only one of the systems. In order to train our supervised models, we need to calculate some features, and we propose sets of features that can be easily computed for any arbitrary corpora. Based on observations from related works of entity linking that study the factors which affect the performance of the systems, we have proposed some features from the following categories: the surface form-based features, which relate to the word or sequence of words representing an entity; mention-based features, which relate to the mention recognized in the document in a specific position; and document-based features, which relate to the document containing the mention. Since more than one system can provide the correct entity link for a mention, we model the problem as a multi-label classification task, where multiple labels, in our case multiple systems, may be assigned to each instance. Multi-label classification can be categorized in two major groups. The first one is the problem transformation methods, and the second one is the algorithm adaptation methods. Even though we have experimented with a great variety of methods, we just report the results from the best performing methods, which is the binary relevance method using the random forest as a base classifier. As regards the case where only one system has recognized the mention, the strict approach needs to predict if the entity link is correct. So for that we need n binary classification models, one for each of the considered entity linking system. So we have also experimented with a great number of classifiers such as SVM, naive-Bayes, logistic regression, decision tree, random forest, SMO, and multi-layer perceptron, and we also report the best performing method, which is the sequential minimal optimization. For training supervised classifiers on the prediction tasks, one can generate instances using manual labeling, crowdsourcing, or existing ground truth datasets. In our experiments, we use existing ground truth datasets, and after we annotate the documents of the training corpus, we also compute the features values for each mention that also exists in the ground truth and assign the corresponding class label. For the multi-label classifier, we label the training instances by simply considering the systems that managed to correctly disambiguate the mention. And for each binary classifier, we make use of only the annotations produced by the corresponding entity linking tool and label the training instances as either true or false. We've used the following three datasets, which have at least 1000 training annotations: CONAL, for example, IITB, and NIL. Both CONAL and NIL are already split into training and test sets, but for IITB we consider the first 90% of the provided annotations for training our models and the remaining 10% for testing. The table to the right shows some statistics about the annotations. We've adopted these three popular tools, Ambiverse, Babelfy, and TagMe, because they are end-to-end and ready-made tools that can be easily used out of the box, and they are also accessible through public APIs without the requirement of further configurations and tuning. Since the objective of the meta-entity linking is the selection of output from multiple tools for achieving a better performance, each of the used tools can be considered as a naive baseline. Another baseline that we've used is the random one, which selects one of the tools randomly, the best system as well, which selects the link provided by the system with the highest overall performance in the ground truth dataset, and a majority plus random, which selects the link provided by the majority of the tools, and if all the tools provide a different link, a random one is selected. Another baseline is the majority plus best, which selects the link provided by the majority of the tools, and if all the tools provide a different link, the system with the highest overall performance is selected. weighted voting scheme as well, in which the annotations are combined through the weighted voting scheme described in Ruiz and Bobo. But if the score is lower than the maximum precision for all the annotators on the ranking corpus, the annotation is not considered. And finally, the weighted voting all, in which the annotations are combined through the weighted voting scheme described above, but in this case, we don't filter out annotations with a score lower than the maximum precision for all mentions. We've compared the performance of the previously mentioned baselines with the following two approaches: meta-entity linking plus loose, in which you use a multi-label binary relevance classifier with a random force as a base classifier, and the second one is the meta-entity linking plus strict, which is the same multi-label classifier from the loose approach, but in this case, the method is more selective, and when a mention is recognized by only one of the systems, a system-specific SMO binary classifier is used for predicting if the entity link is correct or not. For evaluating our proposed methods, we make use of the following metrics. In the case of the entity linking performance, we use the traditional precision recall and F-score. And to evaluate the classification performance, in the case of the single label classifier, we use the accuracy and the per class precision recall and F-score. And on the multi-label classification, we use the Hamming loss, Jacquard index, exact match, and per class precision recall and F-score. Now I'm going to show you some annotation statistics that were created by the three tools employed in our work. The first four rows show the total number of ground truth annotations from each dataset and the number of annotations that were produced by each of the considered entity linking tools. The next rows show the number of ground truth mentions recognized by 0, only 1, 2, or all three tools, as well as the number of mentions for which at least one of the tools provides the correct entity and the agreement of the tools in the provided entities. Now, to the entity linking performance results. In this table, we can see the performance of all approaches calculated on the different datasets. In the first row, we can see the upper bound performance. The upper bound performance is calculated as being an ideal meta-entity linking system that always makes a correct prediction, and thus no other method can provide better results. The next three rows show the performance of each individual entity linking tool. The next 6 rows show the performance of the 6 baselines proposed in our work, and the last 2 rows the performance of our meta-entity linking methods, both loose and strict approaches. First, we notice that the performance of the individual entity linking tools varies across datasets. As regards CONOL, Babelfy is the top performing one, for IITB Ambiverse is the top performing tool, and for NIL, TAGME is the tool with the best performance. This validates our motivation that the performance of systems varies across datasets. As regards the performance of the proposed meta-entity linking approaches, we've seen that our loose approach achieves the highest F-score in CONOL, outperforming the top-performing individual system by 10 percentage points and the top-performing baseline by 5 percentage points. And finally, for NIL, we notice that our loose approach and 4 of the baseline systems achieve the same performance. Well, this is not surprising given the very small number of cases that need prediction. Here, we show the performance results from the prediction task. The table on the left shows the results from the multi-label classification, and the table on the right shows the results from the binary classification task. In the case of the multi-label classification, we can see that Jacquard index is high for CONOL and IITB, but low for NIL, followed by the Hamming loss and the exact match. In the following rows, we look at the per class performance. We see that for CONOL, the label class Babelfy achieves the highest F-score, And on the contrary, for IITB, the ambiverse class achieves the highest F-score. Yet, for nil, the highest F-score is again achieved by ambiverse class. The table on the right shows the performance of the three binary classifiers used in our strict method. First, we should highlight that the class distribution is very unbalanced. On average, around 78% of the annotations are correct and labeled as the true class, and 22% are wrong, labeled as false class. So that means the false class is underrepresented, which makes the classification problem harder. But as it was expected, we've noticed that the precision is very high for the majority true classes in almost all cases, while recall is high for the minority false classes. In this table here, we can see the performance for different combinations of features when considering the largest ground truth dataset, in our case Conalol, and the best performing meta-entity linking approach, which was meta-entity linking plus loose. With respect to the categories of features, we've seen that the best performance is achieved when all the categories are combined together. That means that all contribute on achieving a very high performance. Regarding each individual category, we've noticed that the surface form-based features have the best performance, achieving an F1 score of 80.4%. And regarding the influence of each individual feature, we've noticed that the S ratio has the highest effect when we exclude it, dropping the F1 score. In summary, we've seen that combining multiple tools through the meta-entity linking approach can achieve a better performance than each individual systems in isolation, and the proposed supervised ensemble method significantly outperforms the individual entity linking tools as well as 6 baseline methods in the largest and most reliable dataset. Our strict approach, which predicts if the provided link is correct, can further improve precision without significantly affecting recall. And the proposed multi-label classifier achieves a precision accuracy of greater than 90% in the two largest datasets from our evaluation. And we have also seen that all the three categories of features contribute to achieving the highest performance. Limitations of our work are basically concerned with the limited performance of the binary classifiers in the strict approach and the need for corpus-specific training data. Finally, some conclusions. We've argued that the performance of entity linking on a given corpus may be optimized by combining the results of distinct entity linking tools, and to this end, we've introduced a novel approach towards meta-entity linking where the outputs of multiple end-to-end systems are unified on a per-mention basis through an ensemble learning approach. We've modeled the problem as a supervised classification task, and we've provided a rich set of features that can be used within a supervised classifier for predicting the system that can provide the correct link for a given mention. Considering the largest ground truth dataset, our multi-label classifier outperforms the F-score of both the best performing individual entity linking system by around 10 percentage points and the best baseline method by around 5 percentage points. And finally, an extensive feature analysis showed that almost all the proposed features contribute on achieving the highest performance. Given the promising results from our experiments in the future, we plan to extensively evaluate the performance gain of meta-entity linking using different numbers and combinations of tools, including the more recent tools that make use of neural networks. We also intend to study distantly supervised approaches, aiming at solving the problem of obtaining corpus-specific data. And finally, we plan to investigate the applicability of more advanced models for the binary classification task. That concludes my presentation, and I appreciate for your time and attention. Thank you.